yesterday in my email, we're going to have 2 Blackboard talks before the winter break. And so it's the first time we test this device. I think it's going to work well, but don't hesitate to tell us if there is an issue with the sound or anything. That being said, we are very fortunate for Tomas, who's going to tell us more about secular transformational theory. So if you're ready, take it away.
Awesome. Thank you very much, Anton. And thank you very much to all of you for this very nice talk. Please interrupt me as many times as possible in order to make this clear. I really want to convey the message in the clearest way possible. And it will be a little bit bugging to move on and on without things being more or less understood. So please interrupt me as many times as you need in order to make things clear. This is a little bit of the plan of the talk that I'm about to show you. First and foremost, what is the real need to even talk about secular perturbation theory, and what is the phenomena that we are particularly interested in approaching? Second, what follows from there goes a little bit like a tutorial. We are trying to solve and work out together a very nice problem that shows many features about the problems of naive perturbation theory and how can certain things be remediated by taking a renormalization approach. The other thing that I want to tell you about is about operations that one can do in parameter space. Potentially time evolution of parameters as well as reparameterizations that one goes along the way. It happens that parameter space has a very nice and rich geometrical structure, which would be very interesting to try to exploit and to use for our convenience. The other thing that follows is to try to learn how to displace in parameter space. By that, we're going to generate beta functions. We represent time evolution, which are going to be the generators of time evolution in parameter space, and alpha functions, this is a funny name, that we provide for generating reparameterizations along the way. That means to change the identity of the parameters as one moves in time evolution. Then one of the last things to do is, okay, how can we build a more or less decent first order perturbative solution? And then we compare with the full nice solution of the damped KDV problem. So yeah, for things like that, the whole community of general relativity and strong gravity got very excited since 2017. Many talks and many colloquia and many presentations have been, let's say, injected with enthusiasm since these years, because gravity stopped becoming this very kind of obscure and just mainly theoretical field, and just started to gain life as a more observational and more interestingly contrasted phenomenology that we can all take into account. The improvement on detection of general gravitational waves is going to lead us to distinguish more and more if we are allowed to have something that deviates ever so slightly from standard general relativity. It is true, constraints are quite tough for many ideas that people have tossed around about what are the possible modifications to a theory of gravity, but the suspicion is that there might be, we hope, some room to actually see if there's any chance of having, if it's possible to accommodate certain corrections. And I would say that many people will be on the boat of trying to modify gravity, not only people that are interested in some quantum nice limit of a theory of general relativity, but also people that are interested in understanding what happens with dark matter or dark energy. Cosmological motivations also come from there. So I think that before even trying to say something like that, let me stop sharing my screen and show you a little bit of what people usually understand. Okay. How can I go back? My mouse just disappeared. Can you give me a moment? Stop sharing. Good. Okay, so I hope everyone can. Hey, can everyone see the board?
It looks good to me. I'm not sure
It's
about
good?
anyone else.
It's
good.
Good. So we're going to test, or more or less put into the presentation, a couple of flavors of modified theories of gravity. The first one comes from what people call Einstein-Dilaton-Gauss-Bonnet gravity, which is Einstein-Hilbert action, an extra scalar field, and non-minimal coupling of this extra scalar field with the old and very well-known Gauss-Bonnet invariant. And the second flavor of it, which is quite related to the first one, is what people call dynamical Kern-Simons theory, which looks pretty much the same, apart from one term that is slightly different, that has coupling of the Riemann tensor with its dual, generating what people call the Pontiac density. So these are nice examples of non-minimally coupled scalar tensor theories of gravity. And it will be very interesting to try to reconstruct what would be potential gravitational wave profiles that coming out of those. Yes.
Yeah, so I'm just so I'm not a cosmologist. I'm just trying to understand physically the difference between these two theories. So it looks like there is a scalar field in both, right? So that's just an energy density that's kind of permeates all space. That's the thing that both the theories have the same.
Yes, that's what is going on.
Okay.
There's an extra force showing up in there.
Okay, and then looking at these two different things. So let's see here. So the first looks like there's a scalar function, which is a function of the scalar field multiplied by the Einstein tensor. And the second, what's the second term? So are those R's both like the determinant of the tensor?
No.
Or
okay, RGB, this,
okay,
let's say calligraphic R, is just the Gauss-Bonnet invariant.
Okay.
This is a topological invariant of general relativity.
Okay.
The second thing is a slightly different quantity. It's called the Pontiac density. Also, it's also an example of a non-minimally coupled theory of gravity. Non-minimally coupled scalar field with gravity, and instead of coupling Riemann and Riemann, it couplings Riemann and dual Riemann.
Okay. So it's a slight thing in that it couples instead with the regular Riemann tensor, the dual of the Riemann tensor.
Naively speaking, if one wants to be like plain and very vague of it, think of it as F dual.
Okay. So it's like a dual of the theory that you're. Okay.
There you go. Exactly. You're talking about some transverse mode that appears in there, and it's, let's say, it's directly coupled to the scalar field, almost as if you gain like approack-like term for the other.
Okay, that makes sense. Yeah. Thank you. Yep.
No problem. So then let me go back to more or less what the state in which people try to do certain things. So see if I can just share my screen again. Good. So, sharing the screen. Great. So this is more or less the typical approach that people do in order to actually follow standard perturbation theory. In this kind of theories, I need to say in advance that initial value problem is not, people are not sure that initial value problem is well posed for these theories, but the reason for which this is this might not be well posed is because the theory might not be true. Let's understand that these theories come from truncation in a let's say larger and more complicated effective field theory. So what one wants to understand is what these corrections do to the gravitational wave profile. And in order to understand what those corrections do, one has to decompose around a background metric and also a background value of the extra scalar field. Then one has a very nice set of equations that allows us to see, okay, there's a first order perturbation theory, a linearized system, and let's say the corresponding linearized system that appears for the scalar field. And when one wants to initialize the merging process of two black holes, one notices that as one takes further and further distance between the two merging black holes, what tends to happen is that the generated gravitational wave profile starts to diverge as one allows the merger to begin earlier and earlier. That can be seen in the figure that I'm showing you in the right panel.
Sorry.
Yes.
Yeah, so with the equations in the yellow box, so I think I understand why all of the other terms have subscript, because you're perturbing the perturbation in the scalar field and the background gravity.
Yes.
But it looks like you also are perturbing, I forget the name of the box thing. It's basically the partial derivatives to the second power when you're looking at space-time. So are you perturbing also, are there length scales or time scales which are small, which are also perturbing in this problem? Or
what happens is that since you're introducing corrections that are of order Riemann, when you integrate equations of motion, you're going to get corrections of the scalar field equation that are going to introduce something like that naively is going to look like box squared in equations of motion. So you're going to introduce like higher derivative corrections in phi in the scalar. If you do integration by parts of either this or this and try to integrate out with respect to the counting of theta, you're going to get eventually, as you progress in perturbation theory, you're going to get further corrections of what box is.
Thank you. Yep.
And of course, those corrections for the realities are going to be modulated by the strength of alpha GB and DCS, right? So the smaller these parameters are, the smaller the correction that you're going to drag along for those length scales. So essentially, and this is what I'm here to talk to you about, when you evaluate the problem of the merger, either by doing this very complicated perturbative expansion, or either just by doing post-Victorian analysis, what you're going to find is that the further you put the two objects that are going to merge, the outcoming gravitational wave is going to gain amplitude as you go further and further. So that over there is a signal of secular growth. It does not only happen in a system that is as complicated as this. It can happen for, let's say, when you start to introduce corrections to nonlinear equations, such as sine Gordon or as KDV, which I'm about to show you right now. When you introduce further corrections to these things and just do resummation of naive perturbation theory, what is going to happen is that with sufficient time, the solution that you get to equations of motion are going to diverge. So instead of doing this complicated problem of treating the full perturbative expansion of a modified theory of gravity, let me show you a slightly simpler problem that has to do with something that we might be kind of familiar, and it's something that, I don't know, we as physicists kind of like, and we were shown like since earlier courses. Let me show you over there in the very first top of the equation what might be called the perturbed KDV equation. What is this? What is the thing that perturbed the KDV equation? Is the presence of this extra damping term in the orange rectangle that you can see over there. You introduce a small damping factor. If you are a little bit attached and you have very close to you introducing damping terms in harmonic oscillators, this is going to look slightly different because what you're doing is, again, you're trying to modify equation of motion with higher derivatives. And in order to have something that has the same damping effects, you have to flip the sign of the correction. The thing on the green rectangle now is your good and old and beloved KdV equation. For that, the soluble solution of that is well known. Let me proceed, and before that, let's proceed with that, and then I'm going to show you a little bit more about how the solution for that looks like. And in principle, the problem that I have chosen to show you is a problem that either, let's say, in its first presentation with the perturbed equation, can be solved numerically without an issue. So in principle, I'm going to cheat for the convenience of the presentation. It is not impossible to actually figure out solutions for the perturbed KdV equation. So it is perfectly possible to actually compare if we had any level of success in trying to produce a first order perturbative solution. And in the yellow rectangle, finally, I'm going to introduce to you a perturbation, a first order perturbation to the KdV solution, which contains the first evidence of that. KdV1, I think I made an error in the upper subscript of that. I should have called it KdV0. It's a linear operator acting on the first order perturbation, and S phi 0 is just an external source term. So let's look at.
So just before you move on, I have a question. Can you move back?
Yes.
So I'm trying to understand the first order perturbation, the one circled in yellow.
Yes.
So everything that's phi top 1 is higher order in perturbation, but then the S term is 0 order in the perturbation. So
I forgot to multiply that thing by phi 1 in the front.
I see.
You're
I see.
absolutely right. The source term acts multiplicatively on phi 1. Yes.
Okay. Now it makes sense. Thank you.
Yes. So on the left-hand side, you can see very nice evolution of background KdV solution. It's just a solitary wave that propagates freely through space. And on the right panel, I'm showing you the full numerical solution of the perturbed KdV equation, which damps in time and leaves a tail behind it as it propagates through space. Imagine you can have like a rough picture of it, like as if it were a bubble propagating through, let's say, you have a bubble made of soap, and eventually as it moves throughout the surface, it leaves soap behind it. And as it moves, it's going to leave, let's say, a small film of soap. And that small field of soap is that very small step that you see that is generated as long as the solution propagates. It's very nice because the background solution can be written in a very nice closed form. So before even trying to do that, let me show you more or less what's the actual problem and why we actually care about that. So if we do naive perturbation theory, which implies saying that the full solution is something like the background solution plus epsilon times the first order correction, what is going to happen is that up to some amount of time, the solution is going to work well. Eventually, you're going to see even decay of the solution. But if you wait for sufficiently long, eventually the solution will break. The amplitude will break and the phase will break. The first thing that is going to break is the amplitude. It breaks linearly in time. The second thing that is going to break is the phase. It breaks quadratically in time. So there you have, lo and behold, why at some order how perturbation, like a naive application of a perturbative scheme breaks it. So the question will be how to generate a solution that doesn't break. Yeah, it goes up. So the idea is the following. considering and knowing what is the original background solitary solution. That which I showed you on the left panel here. This very nice solitary wave that moves is completely in outer. Well, there is a nice analytic solution for that. It happens to depend only on one parameter and the position of the peak. That's given by second hyperbolic square. Very nice solitary peak that just moves with speed v and amplitude v over 2 and width equal to 1 over, well, 2 over square root of v. That's going to be the width of the peak. So I'm posing you a very interesting problem. And the problem is the following. What happens if we try to build an approximate solution by just changing what is only parameter, called v in this case, by a time-dependent function? Is it possible that these time-dependent functions, once replaced in the original solution, capture some of the behavior of the total solution, generating a solution that by itself does not break in time? Can we get something that decently looks like a first-order perturbative solution? To do so, what we're going to try to do is to try to generate a small map, and this map tries to, let's say, map deformations in functional space, noticing that the first order perturbative solution can be interpreted as a generator of deformations in solution space, and do a map of that into parameter space, and try to see if one can map an infinite dimensional space of deformations into a finite dimensional space by doing two things: allowing the parameters to time evolve. That is going to be what the beta functions are going to do. The beta functions are going to represent what the evolution of the parameters is going to be, and also trying at the same time to reparameterize these parameters as one moves across the full solution. As one deforms the full solution, right? The reason for which I'm postulating these forms of the two parameters b and xc, I hope that you notice that there's absolutely anything mysterious in what I'm doing with the peak position. What I'm saying is, okay, guys, it moves with constant acceleration and it's linear in time. Naively. It's just, okay, constant acceleration and linear in time for velocity. That seems to be, let's say, a naive first order assumption of how these things might be. So if we can construct a full solution out of this reparameterization, and also considering that you're also deforming in functional space, and let's try to glue those changes all together. How do we do that? Well, this is more or less a schematic of what I'm trying to tell you about. Okay, you have deformations in functional space. They act on every single point of the solution, and on the left-hand side, you have deformations in parameter space. These shift parameters and time evolve them as they move. I hope that it does not get upset with me, but these are very nice problem of transport in parameter space and its lead transport. And essentially, it's going to be you're going to have lead brackets of alpha and beta acting successively on them, which is going to give you this house of this very nice symbol separation that you do in quantum mechanics to try to represent exponential operators via commutators. Hope you guys remember your quantum mechanics and try to do this commutator expansion. That's more or less the same structure that underlies underneath these motions in parameter space. So yes, that's the idea, mapping transformations in functional space to transformations in parameter space. And what we're going to demand to do so is that the full derivative, like the functional derivative of the total solution as a function of the deformation that one can achieve has to be minimal. And this implies two things. If this is true, the derivative of the full solution with respect to epsilon in functional space is just going to give you the generator of deformations in such space, which is simply just the first order perturbative solution. Phi 1. Let me go back a few steps backwards for you. Yes. 1, 2, 3, 4th line, the very thing that is on the right. Yes. If you take the derivative of that with respect to bar epsilon, you're going to get phi 1, right? Yes. That's what you're going to get. So that's what I'm saying here. That's all I'm saying here. The derivative with respect of the full solution with respect to bar epsilon is phi 1. Cool. The thing that follows below is if you take derivative, the same derivative with respect to acting on this solution, which is the final thing that I wrote in the last line of this slide. So here I'm actually trying to marry deformations in parameter space with deformations in functional space. Okay? Good. And I want that difference to be minimal. Therefore, what I've done with this is generating a cost function. It's a cost function that is going to work for every single choice of initial parameter that I do on the system. That expression that I have over there has to be minimum in all points. So therefore, what I actually need to minimize, yes, same old, orange rectangle, deformations in functional space, yellow rectangle, deformations in parameter space. So what I actually need to minimize is this integral over here. So I have generated this function now, which depends quadratically on alpha and beta. And my function now is going to look like a very nice quadratic form, assuming that the time needed to evolve the parameters is going to be much larger than the time that I need to evolve the full solution. This is very similar to the language that one uses in renormalization theory, in which one assumes that the time that it takes for parameters in the theory to evolve is sufficient, is much larger than the whole dynamics of the system that underlies, right? Minimizing that full function is not very complicated. If I want to minimize that thing with respect to alpha and beta, you have quadratic function on alpha and beta, linear function, constant. Take the derivative of your object with respect to alpha and beta, and you have this very nice structure over here. The recipe for the problem is to repeat that for every single initial choice of parameters. So therefore, what do I need? I'm going to be able to write that functional I for every choice of parameters that I have. Let's go back to the original KDV problem. This only means the following. I'm going to take different solutions of phi 0 for different values of v. And I'm going to initialize this thing over here for each one of those values. So I'm going to get corresponding values of alpha and beta for all of the different values of v that I'm going to have. Okay? And if I've done the job properly, and I found values of alpha and beta that do the trick for me, then what I have essentially done is to, okay, based on just taking derivatives of the background solution, I managed to reconstruct the first order perturbative solution just completely out of the derivatives of the background solution with respect to parameters. So this means the following. If I have absolutely no clue on what is the dependence of time on the full solution, what I could have done is to say, okay, I have no idea what that solution looks like. Let me try with some polynomial. Okay, I take my polynomial, right? And the objective is trying to reconstruct out of derivatives of that out of derivatives of the background solution, what is the best fit possible to the first order perturbative solution. And if I've done that well, then I have convenient values of all the generators of translation in parameter space. And if I have overshot and I have completely overestimated the number of parameters that I have, I'm going to have a huge null space. So I'm going to have a lot of combinations that are going to be just redundant. Okay, so the method by itself is going to preclude, and you're going to notice this in a very simple way. If you start to take off parameters in your initial guess, and you start to see that the value of R squared in your fitting of the perturbative solution is the same, therefore you have found a redundant parameter. So it runs diagnostics on itself. Let me show you something before that. The thing on the left panel I think is interesting, and I think it's important for you guys to notice. You see this very nice step being growing as time goes by. And let me take you back to the original solution of the full problem. Do you remember that I told you about this thing of the bubble that just leaves a thing behind it as it moves through space? Well, that over there can be reconstructed by taking into account what is this function, or this function here called the perturbative, the particular solution which I try to minimize. So therefore, for this perturbative approach, it's not sufficient to just calculate values of alpha and beta. There is an important part of information that also comes from the particular solution. If you're going to ask me, how do I combine those two pieces of information to give the full solution? The answer that I have to give you is, I don't know. Okay, so this is a good refresher of what actually happens. So the thing that I tried to convince you at the beginning that was somehow due to a nonlinear effect of a bubble just dissolving through space, it happens to be more or less reconstructed with, let's say in a rough approximation by these steps being formed by the particular solution to that very nice functional that I construct, this cost functional that I showed you about. So, okay, once I found values of alpha and beta as functions of the original parameters V, therefore I have evolution equations for what the parameters are as functions of time. The full evolution has a very nice dragging term. The dragging term tells you that there is a possibility of time evolving and reparameterizing along the way. And that's given by the bracket of alpha and beta. What happens at first order perturbation theory is that term is supposed to be a small correction. The truth is that actually you have to actually take a closer look on what the values of alpha and beta are. So actually see if these are going to be small corrections or not. All what I'm saying here is that if we follow this prescription, doing second order perturbation theory is much harder than just expanding things up to epsilon squared in solution space. The transport term is going to do something else, and that something else is going to be partially reflected on this transport, on this extra transport term that appears in the equation of motion. For the sake of just first order perturbation theory, I'm only going to assume that the role of alpha is just to change initial conditions for the parameters to evolve in time. That's all what I'm going to get that they're going to do at first order. So take home message is that, okay, second, third, fourth order perturbation theory is much more complicated than just expanding up to whatever power of epsilon you want. That's, if you learn that from this position, I'm happy. Okay, so you after running a bunch of evolution, after running a bunch of simulations and trying to figure what the values of alpha and beta are as functions of V, we happen to have that the slope, when you look at log V, log beta, behaves very nice, like a very nice and round critical exponent of 2 for beta. So that means that dV/dt runs as beta squared. And the other one runs as 0.52. That I don't have a number from the bottom of my head that can really connect to that one. Let me follow with the story. Oh, by the way, yeah, you can think, are those error bars? Why are you showing such a big round cloud around the point? Well, I took very large covariance matrix to just show you what is the impact of numerical error in your solutions. I just multiplied covariance matrix by 1,000 for this, in order for you to see what are the points that are more susceptible to error from my simulation. So, yeah, that's the way it goes. So this is more or less what you should expect for what are the errors in slope and intercept of the linear function to represent how beta and alpha are as functions of V. We have error bars for all of those. There's also convergence clause that more or less show what we should expect. What should one expect for different resolutions of the simulations run. So it is possible to do propagation of errors with this. It's more or less safe to be done. The errors are fairly small in this case, as you can more or less tell in the plots there. Is that I just made an effort to make it readable. Okay. So one of the things that one can do, one has obtained what beta and alpha are, is to reconstruct what are the amplitude, the width, and the position of the peak as functions of time compared to the ones of the full solution. And okay, the original offset that you're going to see at t equals 0, comes just because I reparameterize. I pick actually different values of alpha for each one of those. So there's going to be a small offset at t equals 0 because of those. The error that I'm getting for the shift of the peak position is quadratic in epsilon, which will be very happy because that means that these are second order effects. It's okay. Okay, so black curve is the full nonlinear solution, or purple curve is the naive perturbative scheme, and blue curve is my full solution obtained by this fancy method I tried to convince you in school. Hopefully you see in school. So, yeah. So your perturbative solution blows up very rapidly, and your naive and your renormalized solution stays very close. So it's a good starting point. So the next question to answer is what happens if one allows different parameterization of the same thing? And the answer is the same. If you take different parameterizations of the same problem, they are going to converge to your original answer. If you remember, the amplitude was a function of B at the beginning, the width the same, the peak position the same. So I actually allow these to be independent parameters. And if one continues and tries to resolve alpha and beta functions for all of those, one happens to find that the flow of the independent parameters is consistent with the original flow that only depends on one parameter. So that's more or less a consistency check. That if you, let's say, naively introduce more dimensions in the problem, is going to go back to its original preferred parameterization. So that's a very nice alpha check of the problem. It's pretty nice. The others are very small. This is the other thing that is kind of neat, and is that when you actually compute what the beta functions might be from the full solution and compare it with the actual beta functions that you computed from this procedure, it turns out that for smaller and smaller and smaller values of epsilon, you see very nice convergence to the solution. The nice contour plot that you see on the bottom represents the spread in parameter space at different values of epsilon. So the bigger the value of epsilon, the more dissimilar are going to be the flow of these 3 or 4 parameters that I showed you. And by 3 or 4 parameters, I mean the amplitude, the width, the peak position, as if these were independent parameters. Here's another interesting check that I wanted to share with you, and it's the following. The values of alpha and beta do depend on how long you allow the simulation to run. This is a non-local calculation. You, in principle, need to evolve your perturbative scheme for as long as you can. The idea is that eventually the values of alpha and beta should converge as long as you allow the time of running the simulation to be longer and longer. And for all the values of beta, you see a very clear convergence. But for the values of alpha, you see that there is no convergence. And that is actually telling us that we screwed up with parameterization derivatives. And that can be seen because the very nice convergence clause that I showed you about beta functions does not replicate the same for alphas. You do not see the same convergence as alpha becomes smaller. But still, if you completely ignore the presence of the reparameterizations from the very beginning, your solution is going to be worse by a factor of 20%. So, yes, your solution for reparameterizations is not perfect. But yes, the value that you got in there is going to do something. So please keep it. That's all. Thank you very much.
Thank you.
Thank you very much for presenting.
Thanks to you for listening to me. Do you have any question?
Yeah, so I have a question. So what if I understand correctly, the problem that you ran into here that prompted all this derivation is similar to something that happens in calculation of asteroid Molland, right? If you just use the regular coordinate as position, then you run into this problem when you try to do perturbation theory, but you run into a perturbation, but your perturbation diverges, right? Because if you're close to the edge of a star and the star moves a little bit, then you find yourself outside the star and you have a perturbation of 100%. The solution there is, instead of using the special coordinate, they use mass coordinates, so Lagrangian. So I was wondering, in the context of a KDV, can't you use one of the conserved quantities, like the mass or momentum or energy, and use that as a coordinate and circumvent the difficulty that you run into, instead of, maybe it's equivalent to the derivation that you've presented here, where you model the displacement.
I do suspect that you're right, and but the thing is the following: when you introduce this perturbation term, most of the conserved quantities that KDV had from the beginning became no longer conserved. So it becomes like, for the perturbed KDV problem, it becomes harder to keep track on up to what extent these conserved quantities are going to respond if I try to do some form of evolution equation. My suspicion is that, again, but if these deviations happen to be small, then in principle you're right. You can actually trace back and try to see if any of the conserved quantities can be matched up with the parameters that I'm trying to present in here. So my suspicion is that yes, you're right. In principle, I do suspect that within, let's say, small values of the perturbations, it is very possible to trace back the conserved quantities and actually try to see if these parameters can be phrased in terms of those, and then find a question model for them. That would be a way to do it. But here's the thing: in principle, in a generic problem that doesn't have as much symmetries as KDV, that becomes increasingly hard, right? When I introduce this mess in modified gravity, don't even think about that. It's like, trying to generate those is going to become harder. The other thing that I think is kind of interesting to take into account is that if I've done my homework correctly, instead of expanding about the original KDV solution, what happens if I expand around the renormalized solution of KDV? My suspicion is that things might improve quite a bit. So what I'm saying is the following. Back. So instead of using phi 0 to calculate the perturbative solution in the yellow rectangle solution, what I'm going to do is actually go and replace it by phi rem, which I just obtained from doing the Reconstructing. In principle, my expectation is that that new solution around that point might not diverge. I still haven't tried that, but maybe it would be interesting to check, because there's no reason to believe that the actual the final solution should be significantly far from this. So yeah, that can happen. Any more questions? Curses?
All right. Thanks everyone for coming. Next talk will be February, December 15th, and it will be a talk given by Chris Matt. So I will let you know what's the subject. And have a wonderful day.
Thank you very much.